Hello students, today we discuss about ideal solutions, deviation from ideal behavior, that is non-ideal solution, and azeotropes. First come to the ideal solutions. The solutions which obey Raoult's law over the entire range of concentration are known as ideal solutions. And as we have discussed, what is Raoult's law? That is, partial vapor pressure of each component is directly proportional to its mole fraction. And mathematically, we can write P1 is equal to P naught 1 multiplied by x1, P2 is equal to P naught 2 x2, and that's why P total is P1 plus P2. The two characteristics of ideal solutions are enthalpy of mixing of pure components to form the solution is 0, and the volume of mixing is also 0. We can say that is delta H mixing is 0 and delta V mixing is 0. Now what is the meaning of these two? That is, no heat is absorbed or evolved when the components are mixed, and volume of solution would be equal to the sum of volumes of the two components. It means if we are mixing 10 ml of component 1 and 10 ml of component 2, then the volume of solution will be 10 plus 10 is equal to 20 ml. But what about at molecular level? If we consider the two components A and B, then if these components are pure, then there are the intermolecular attractive interactions will be of types AA in the component A and BB in component B. Whereas binary solution, in addition to these two interactions, AB types of interaction will also be present. Simply we can say this: if we say A is a solute and B is a solvent. So in component A, there is a force of attraction between the solute molecule is referred as a AA interaction. And in case of solvent, this is referred as BB interaction. Now, when we are mixing these two, so some new interactions will also become, that is interaction between solute and solvent. If this interaction between solute and solvent is similar to the solute-solute interaction and solvent-solvent interaction, then this is called ideal solution. If the intermolecular attractive forces between AA and BB are nearly equal to those between AB, this leads to the formation of ideal solution. 100% ideal solutions are rare, but some mixtures or solutions may behave as nearly ideal solutions. Examples like these: solution of normal hexane and normal heptane, solution of bromoethane and chloroethane, solution of benzene and toluene. These are the some nearly ideal solutions. Now, what about non-ideal solutions? When a solution does not obey Raoult's law over the entire range of concentration, then it is called non-ideal solution. In case of non-ideal solution, the vapor pressure is either higher or lower than that predicted by Raoult's law. If it is higher, then solution exhibits positive deviation, and if it is lower, it exhibits negative deviation. Now we can compare these two type of solution, that is solution which exhibits positive deviation and solution which exhibits negative deviation. As we discussed, vapor pressure is higher than that predicted by Raoult's law. Mathematically, we can write that is this vapor pressure of the solution is higher than these product of these two terms. In the same way, vapor pressure of the component 2 is higher than the product of these two. So that's why we can say P total is higher than sum of P1 plus P2 as predicted by the Raoult's law. In the positive deviation, delta H mixing is greater than 0, that is positive, and delta V mixing is greater than 0, that is this is also positive. What about at molecular level? In this case, the AB type of interactions are smaller than AA and BB type interactions. It means when we mix the A and B, new interactions arises between A and B, that is AB type interaction. The magnitude of this AB type interaction is lower than AA and BB. That's why from this solution, the molecules can escape easily and form more vapors. That's why their vapor pressure is higher. Examples are ethanol and acetone, mixture of ethanol and acetone. In case of ethanol, hydrogen bond is there, but when we mix the acetone, the acetone molecule fit in between the ethanol molecule and the magnitude of hydrogen bond is become less. That's why vapor pressure become high. The same way, mixture of carbon dioxide and acetone. Now come to the solution which exhibits negative deviation. In this case, vapor pressure is lower than that predicted by Raoult's law. Lower means that is partial vapor pressure of component 1 is less than product of these two terms. In the same way, partial vapor pressure of component 2 is less than the product of these two terms, and P total is less than sum of P1 and P2 as predicted by the Raoult's law. And delta H mixing is less than 0, that is negative, and delta V mixing is less than 0, that is negative. Now once again try to understand these two terms. Now in this case, delta H mixing is 0. It means that is positive. That is positive. Positive means this is a endothermic process. This is a endothermic process. Heat is absorbed. Heat is absorbed. And delta V mixing is again positive. It means assume 10 ml of component 1 is mixed with the 10 ml of component 2. Then the total volume of the solution will be greater than 20 ml. It may be 20.1, it may be 20.5, depending on the new type of interactions. In the same way, in this case, delta H mixing is less than 0. It means this is negative. This is a exothermic. Heat is released. And this delta V mixing is again less than 0, that is negative. It means if we mix the 10 ml of component 1 with the 10 ml of component 2, then the total volume of such type of solution will be less than 20 ml. Is that clear? Now come to the molecular interactions. In this case, AB type of interactions are higher than AA and BB. That is, new type of interactions will be greater. That's why escapic tendency of the molecules from this solution is less. Less vapors are formed. That's why vapor pressure is lower. See the example, phenol and aniline. As we know, phenol also having the hydrogen bond, aniline also having the hydrogen bond. But when these two are mixed, new hydrogen bonds are formed. Their magnitude is greater than phenol-phenol and aniline-aniline. That's why interaction are greater, vapor pressure is lower. And that is chloroform and acetone. When they are mixed, hydrogen bond are formed. You can say chloroform, formula is CHCl3. Chloroform is CHCl3. And acetone, its formula is CH3COCH3. When we mix them, then between chloroform and acetone, hydrogen bond will form. How this? You can say this is CH, and for this carbon 3 Cl are attached. Clear? Then this acetone can be written as this is C, this is O. For this carbon CH3 is attached, and for this carbon CH3 is attached. Now this attraction between this H of chloroform and oxygen of acetone, this is a hydrogen bond. In individual molecule, that is in chloroform and acetone, hydrogen bond is not there, but when we mix them, hydrogen bond is formed. That's why when interaction is increases, vapor pressure becomes lower. So this is about positive deviation and negative deviation. Mathematically, graphically, we can represent these two like this. So this is positive deviation. This dotted green line represent the ideal solution. This green line, ideal solution. This is the vapor pressure for ideal solution, component 1. This is for component 2. If positive deviation is there, then this is P1 is greater than predicted by the Raoult's law. That's why this become like this increase. This will increase. The same way for this component 2, this is again increase, and that's why total vapor pressure will also more than that predicted by this Raoult's law, positive deviation. Now in case of negative deviation, this again green line represent the ideal condition, and these blue lines represent the negative deviation solution having the negative deviation. That's why this P1 is less than this ideal condition, P2 is also less than this ideal condition, and this is also less than, sorry, this total for the ideal solution, and this line represent for solution with negative deviation. I think this is clear to you. Now next topic will be the azeotrope. But before we discuss the azeotrope, few points, whatever we have discussed in the lower classes, they may be clear. What is the meaning of boiling point? Boiling point is the temperature at which vapor pressure of liquid becomes equal to atmospheric pressure. Is it clear? This we have learnt in lower classes. Now see, in case of positive deviation, there is a one condition is there when vapor pressure of the solution is maximum. Suppose this is the condition where vapor pressure of the solution is maximum. Then if we consider the composition of this mixture which is equal to this one, it means the mixture having this composition will boil at the lower temperature. Try to understand. The mixture having this composition, because its composition having the highest vapor pressure of this solution, if we want to boil this, that's why we have to supply the lower heat. That's why at the low temperature its vapor pressure becomes equal to the atmospheric pressure. That's why this composition have the lower or minimum temperature. Is it clear? In the same way, in this case, that is negative deviation, we can find out one point or one composition where vapor pressure is minimum. So this is the point where vapor pressure is minimum. Then the solution having this composition, like this is the composition of that solution. This solution having this composition, if we want to boil it, then we have to give more heat. That means its boiling point will increase because its vapor pressure is low, and to make this vapor pressure equal to atmospheric pressure, we will give more temperature. That's why this composition will have the higher temperature, higher boiling point. Is it clear? Now where it will useful? Now come to this azeotropes. Binary mixtures having the same composition in liquid and vapor phase and boil at a constant temperature are known as azeotropes. Now try to understand. If we are having the mixture of two different liquids, and as we know different liquids have the different boiling points. When we heat it, vapors will form. Then liquid which has lower boiling point will come more in the vapor phase. It means in the vapor phase, the component which has lower boiling point, its mole fraction will be more. Is it clear? But this is the condition where same composition in liquid and vapor phase. That is, whatever the amount of liquid goes into the vapor phase, in that vapor phase, both component will have the same composition, and both will boil. That is, mixture will boil at the constant temperature. That's why it is not possible to separate the component of azeotropes by fractional distillation. Now just come this fractional distillation. As we know, distillation, this method is used to separate the two liquids having the sufficient difference in their boiling point. Is it clear? And in case of fractional distillation, the difference between the boiling point is smaller, but they have the difference between their boiling point. That's why we are able to separate the two components. But we are saying the azeotropes, that is components of the azeotropes, boil at a constant temperature. That's why with the help of fractional distillation we can't separate them. I think, is it clear? Now again try to understand. When we mix the two components 1 and 2, okay, just take the one example, like if we are taking this ethanol and water, mixture of ethanol and water, as we know boiling point of ethanol is lower than that of water. Is it clear? But at this concentration, that is 95% ethanol, it means 95 ml of ethanol and 5 ml of water. If we are having this mixture, then both ethanol and water will boil at the same temperature. Is it clear now? That's why we can say, now again on the basis of this boiling point, there are the two types of azeotropes called minimum boiling azeotropes, and another one is the maximum boiling azeotropes. Clear? Now the solutions which show a large positive deviation, is it clear? Large positive deviation from Raoult's law form minimum boiling azeotropes, because these type of solutions will boil at the lower boiling point. Is it clear? That's why they are minimum boiling azeotrope. Again remember, this solution should be in the specific composition. If composition is not specific, that will not the example of azeotropes. Like we are saying 95% ethanol in water, it means 95 ml should be ethanol and 5 ml should be water. Another example, the solution that shows large negative deviation from Raoult's law from maximum boiling azeotropes. As already we discussed, the solution with negative deviation from Raoult's law, there is one particular composition, and that solution with particular composition will boil at the maximum boiling point. That's why this will make maximum boiling azeotrope at a specific composition. Again remember, specific composition. Example is 68% nitric acid and 32% water. It means if a volume of solution is 100 ml, then 68 ml is nitric acid and 32 ml is of water. It will boil at the boiling point of 393.5 Kelvin. Is it clear? Now we have discussed about what is ideal solution, what are non-ideal solutions, solution with positive deviation, solution with negative deviation, and what are azeotropes. I hope you have understood this. Thank you.